Predicates and quantifiers. What are they? To express the meaning of such a sentence, every computer connected to the university network is functioning properly. We cannot use simply propositional logic that we have learned so far. We need to use some quantifier that give us the meaning of every. Likewise, can we conclude that if computer 9 is under attack by an intruder, can we conclude that there is some computer in the university which is under attack by the intruder? We don't know whether computer 9 is in the university or not. So we have to use some quantifier saying there exists some computer in the university. So we needed a quantifier of every and there exists. These are quantifiers. And working with such a thing is what we call predicate logic. And to understand the predicate logic, we need to introduce two things. First, we need to know what is a predicate. Two, we need to know the notion of quantifiers, which some of them asserts that for all objects some property is satisfied, and some other asserts that the property is satisfied by one object, one or more, by some object. So certain property is satisfied by all objects or by some object. These are the quantifiers that we are going to learn. So let us start. The statement x is greater than 3. See, it has two parts, the variable x, and the predicate, which we call predicate, is the part is greater than 3. So this part is called predicate and it is denoted P. So the whole sentence P of x denotes the whole sentence x is greater than 3. So this behaves like a function where P, the predicate, is applied to the variable x. So we will call it propositional function. Propositional function P at x. Let's see how that goes. P of 4 means 4 is greater than 3. Now what we do here, we substitute 4 in place of x in this whole statement. So that becomes P of 4 will become 4 is greater than 3. Is that true or false? It is true. So we will make true. Now we substitute 2 for x here, and P of 2 now denotes 2 is greater than 3, and that is false. Now P of 0, now x is 0 here, so P of x denotes 0 is greater than 3, and this is a false statement. One more example. Let Q of x denotes x is greater than 0. And our domain here, this is very important. We are living now here in the domain of the integers. Then what's about P of negative 3? P of negative 3 says negative 3 is greater than 0, which is false. What about P of 0, which says 0 greater than 0, which is false? Now what's about P of 3, which says 3 is greater than 0, and this is true. Again, the same propositional function here is P of x, which denotes the same thing. X is greater than 0. So we go for P of 3, which is true, P of negative 1, which is false. So we have true or false. So the truth value of the whole statement is true. Now again, P of 3 is true. P of negative 1 is false, and we have true and false, and the truth value is false. Again, P of 3 is true, P of negative 1 is false. True gives false, the resulting truth value is false. Here again, P of 3 is true, and this is P of 1 is false, and the negation now becomes true. So true gives true, so the whole truth value is true. Okay. A propositional function may depend on more than one variable, like in this example. So this propositional function depends on two variables, x and y. So q of x and y denotes the statement x equals y plus 3. So what are the truth values of this statement and that one? Okay, now x here is 1 and y is 2. And do these values of x and y satisfy the statement of qxy? Apparently no, because 1 is not equal to 2 plus 3. So the truth value of this statement is false. What about the truth value of this statement here? Now x is 3 and y is 0. And is it true that x 3 and y is 0 plus 3? And the statement is true. Therefore, the truth value of this propositional function is true. Here is an example that uses words. Let C be a variable representing a computer, N representing a network. Now, the propositional function A of Cn denotes that a computer C is connected to a network N. Now, if we have that a computer called Math1 and is connected to network called Campus 2, but not connected to a network called Campus 1, then apparently we will have A of Math1 Campus 1 to be false, because computer Math1 is not connected to network Campus 1, but computer Math1 is connected to network Campus 2, so this is true. Okay. Now again, the propositional functions also could depend on more than two variables, three variables in here. So r of x, y, z denote the statement x plus y equals z. So let us see. For this statement here, this is for x, this is y, and this is z. Now, do these numbers satisfy the above equation? 1 plus 2 indeed equals 3. So the truth value of this propositional function is true, while you can check that the truth value of this propositional function for 001 is false. And in general, propositional functions could depend in a finite number of variables, like this one here. A propositional function on the x and tuple x1 to xn. So this is called a propositional function on this tuple, or it is called n-place predicate or n-ray predicate. As p of x is a propositional function that depends on x, p of x1, x2, all the way to xn is a propositional function that depends in the n-tuple x1 to xn. Okay, now we have learned what is a predicate. Now we will learn what are quantifiers. In here, the area of logic that deals with predicates and the one we learned, and the quantifiers that we will learn is called the predicate calculus, and this is a big topic, a big area. Okay, quantifiers. Quantifiers, the word comes from quantity. So quantifiers is to tell how much or how many is the quantity of things that satisfy certain property. And we are interested in three categories of these quantities. either all elements in the domain satisfy a certain property, or some elements in the domain satisfy that property, or no element satisfy a certain property. So we will look at them. The quantifiers. First kind of quantifiers is the universal quantifier. And this tells that some statement is true, a given statement, a given property is true for all inputs from the domain. So the predicate, I mean by the statement here is the predicate is true for every element under consideration, for every element in the domain. And it is written this way: for every x, p of x, which asserts that p of x is true for every element in a given domain, D. So D will be given as a domain. And it reads as for all x, p of x happen. Or for every x, p of x happen. So to emphasize that, I would like to write it and read it again. For every x, some predicate p of x happen. This is a universal quantifier. And apparently, the universal quantifier here is true whenever p of x is true for every x. This is natural. For every x, p of x is true. And when it is false, whenever there is an element x for which p of x is not true, or p of x is false. So this is easy. For every x, p of x happen. Is it true whenever p of x is true at every x? For every x, p of x happen when this statement is false, when we find an x where p of x does not happen, where p of x is wrong. And let us see examples on that. Example: let p of x denote, if p of x denotes x is greater than 0, and our domain here are integers. Now see that for every x, p of x here is false. It is false indeed. Why? Since now this statement for every x, p of x, it says that for every x integer, x is greater than 0. And this is wrong because p of -1, for example, is false. So there is some element which makes p of x false. So saying for every x, p of x is a false statement. Okay. Again, let p of x here denotes x is greater than 0, but this time you will change the domain to be the set of positive integers. Then for every x, p of x becomes true. So note that this statement here and here, the same quantifier and the predicates, and they are the same as here. So what is changed between part 1 and part 2 of this example? What changed is the domain. Up there was the domain, all the integers, but below here the domain were positive integers only, and that caused every x, p of x is true. Okay. Part 3, what if p of x denotes x is even, and the domain D is the integers? Then for sure, for all x, bx is false. And why? The reason, because I can find an element in the domain, which is 3, belongs to the domain, and f of 3 is false. So it's not true. So I cannot say for every x, p of x is true. This is not so. So the whole statement is wrong because we have one element that makes p of x false. And there is a special name for that element which we call a counterexample. An element for which p of x, every x, p of x is false is called a counterexample. Like what made this statement here false is 3. So 3 is the counterexample. What made this statement here is false is -1, and it will be called negative counterexample. So note that a single counterexample, only one element is enough to say this statement is false. So having one element for x so that p of that element is false makes the whole statement false. Now we will see a counterexample for this, an example, sorry, for a counterexample. Let q of x be the statement that x is less than 2. The domain here are all is the integers. Okay, now note that x equals 3. Note that q of 3 is false. Okay, and 3 belongs to the domain. And that makes every x qx to be a false statement. A false statement, because this is not true for every x in the domain of integers. 3 is an element in that domain, and it does not satisfy q of x. It makes q of x to be false. So x equals 3 is a counterexample. Another one, if p of x is x squared plus 2, where the domain D is the set of integers, then x equals 0 is a counterexample. Why? Because p of 0 is false, and 0 is in the domain. 0 squared is not greater than 0. So since p is false at 0, then for all x, p of x is not a true statement. It is false. And 0 is a counterexample for that quantifier. Every x, p of x. Okay. Now, here again we have the same statement for every x, x squared is greater than x. Now our domain here consists of either real numbers or integers. Now the very same predicate here might take true at a time at some domain and false at some other domain. Let us see. Notice that if we square 1/2, then the result is 1/4, which is less than 1/2. So we have an element whose square is less than itself, and the 1/2 is a real number, belongs to the domain D. So we conclude that for all x, x squared is greater than or equal x is false whenever the domain is real numbers. But it is apparent that if x is an integer, 0, 1, 2, 3, 4, -1, -2, -3, and so on, then its square is greater than the integer itself. So if D is all integers, then this predict with the quantifier every x with x squared greater than or equal x is true. So the same quantifier might be true or false according to the given domain, and this is important. Okay, Now we move to the other quantifier, which is the existential quantifier. So this is quantifier number 2, the existential quantifier. It tells us that a predict is true for one or more elements, but not necessarily for all elements, for one or more. So there exists x such that p of x, that means p of x is true for some x in the domain, and it is read for some x p of x happen. There is an x such that p of x happen. For at least one x, p of x happen. And to emphasize that, let's write it. There is some x such that p of x happen. When this is true, when this statement is true, simply when there is x, that makes p of x true. When it is false, whenever p of x is false for every x, that means there's no value x that makes p true. No such an x. So this is the case where there exists x, bx is false. Okay, let us see examples. Let p of x denote x is greater than 0. Now the domain here is the integers. X is greater than 0 and we live in the integers. So indeed, every x px is true. There exists x p of x, which means there exists an integer such that that integer is positive. Do we have such integer? Yes, because like p of 1 is true. So this is enough to make there exists px such that px happen. Now again here, p of x denotes x less than 0, again one more time, but this time d is the set of positive integers. Now what about, do we have an x, a positive integer such that x is less than 0? We have none. So there exists x p of x is indeed false. Okay, now notice here the same predicate with a quantifier. One time it is false and some other time it is true. And the reason because we changed the domain. We still have the predicate to be the same, but changing the domain might change the truth value. Okay. Now what if x denote x is even, p of x is even, and d, the domain is the integers. Now there exists x such that x is even, where we live in the integers. So do we have an integer such that that integer is even? Yes, we have p of 2. P of 2 is true. So having one true makes that all this to be true. More examples. Let q of x denote the statement x equals x plus 1. Okay. Do we have any real number? The domain here is the real numbers. Any real numbers x such that it equals itself plus 1? This is not possible. There is no such a real number. So that saying there exists x such that qx happens is false. Here we go. No real number is false. Okay. Okay. Okay, now we move to the next quantifier, which I call 3. The uniqueness quantifier. There exists a unique x such that p of x happens. There exists a unique, this is notation for unique, x such that p of x happens. So this means p of x is true only for one and only one x in the domain. And the domain, choosing the domain, plays the role of the truth value of this. So again, there is a unique x such that p of x happens. There is one and only one x such that p of x happens. Let us see here. This example. Let D be the domain of integers. Let p of x denote x plus 1 equals 0. So how many values of integers, how many integers will achieve that? Only the negative 1. So p of negative 1 is true, only 1 is true. So there exists a unique p of x. There exists a unique x such that p of x is true. So another example, p of x denotes x is greater than 0, and still we have the domain D to be the integer. Then this says there exists a unique integer such that this integer is greater than 0, and this is wrong, since so the whole statement is false. And the reason, since we have more than one value that satisfy the predicate p, which is like, for instance, p of 1 is true and p of 2 is true, so more than one value. So there exists unique x such that p of x is false. Okay, now some properties of quantifiers. If we have p of x as a propositional function, then we have seen this before actually. There exists x such that x. For every x such, there exists x such that p of x happen. For every x, p of x happen. The truth value of them depends on the domain. So the truth values of these depend on the domain. For instance, let us see. If D is the set of positive integers, I'm sorry, let me say here that assume we have p of x to be x less than 2 all the way. Okay? For all these cases, 1, 2, and 3. Now, if x is the set of positive integers, then there exists an integer, there exists an x which is less than 2. So this statement is true. There is x such that p of x. This is true because we have at least one, because p of 1 is less than 2. So p of 1 is less than 2, so p of 1 is true. If D is the set of negative integers, then there exists x such that p of x, which means there exists an integer such that that integer is less than 2, is true. Yes, they do exist. And for every negative integer, x is less than 2. Yes, that applies for every. Now remember here, for every means every negative integer. So every negative integer is less than 2 indeed. So this is true. Now, if D consists of 3, 4, and 5 only, so this is a finite domain, 3, 4, and 5. So we will apply p of x to these numbers only. Now, there exists an x such that p of x means there exists an x in D here such that x is less than 2. This is false because the x's we have here is either 3, 4, or 5, and none of them is less than 2. So the statement is false. Now, this says for every x in D, P of x happen. For every x is greater than 2. Yes, because D is 3, 4, and 5. So this statement is true. Okay. Now, as we have seen in the last example, we may have a domain to be finite. In this case, to have this true, to have this true, to have P of x to be true for every x, that means we want to have it to be true at every one of these. To be true here, here, and here. So if every x, P of x is true, that means P of xi is true. And if of every x, P of x is false, that means one of them is false. And we have a conjunction. And if there is an f at any side of the injunction, then the whole truth value is f, is false. Now, same thing applies for there exists an x such that P of x. Now, if this is true, that means one of the P of xi is true, and that causes the disjunction. We know that if we have disjunction, then if we have t at one of the sides, then the whole truth value is t. Good. Now, if we have this to be false, that means P of xi is false for every x. So we will have at all the disjunction, we have false, false, false all the way. So we have the disjunction, all of them to be false. Okay. Let us see here. Let's apply that to the following. Now let P of x be, P of x is the statement x square less than 10, and the domain consists of all positive integers do not exceed 4. So the domain is 1, 2, 3, 4. Now, what is the truth of this statement? For every x, P of x, that means for every x here, x squared is less than 10. Now notice, let us use this to rewrite for every x, P of x means is equivalent to having P of x1 and P of x2 and P of x3 and P of x4. Now, what do we have? P of x1 is true because 1 square is less than 10. P of x2 is true also because 2 square is 4. And I'm sorry, I should write not x1, I mean x1 is 1, x2, x3 is 3, x4 is 4, but I want to write them explicitly here. So I will wait till this thing is erased. Okay. Now we have P of 1 and P of 2 and P of 3 and P of 4. Now P of 1 is true, P of 2 is true, P of 3 is true, but P of 4 square is 16 and it is not less than 2, so it is false. So the truth value of this is false. Now same thing here. In this example, D is 1, 2, 3, and 4. And we use this here to see, rewrite there exists x such that P of x is the same as P of 1 or P of 2 or P of 3 or P of 3 or P of 4. Now P of 1 is false, and I'm sorry, P of 1 is false. Remember here, see here, the statement is P of x squared is greater than 10. 1 square is 1, so this is false. P of 2 square is 4, not greater than 10, so this is false. P of 3 is 9, not greater than 10, false. P of 4 is 16, which is greater than 10, so we have true. So we have false, or false, or false, or true. We have true other side. So this will come out to be the truth value of this is true. Okay, now this is only for a matter of notation, abbreviated notation for unrestricted domain, used to restrict a domain of quantifier. So we will say for every x, but when we identify here that which x, for every x less than 0, the statement is x squared greater than 0. So our domain here is all negative integers. So this is the idea. We abbreviated that by saying for every x less than 0, so for every what? Every x less than 0, we have x squared greater than 0. Same thing here. Now our domain here, for every y which is not 0, so our domain here, all non-zero numbers. All non-zero numbers. For any non-zero number, we have the cubed of that number is not 0. Again, for every z greater than 0, we have z squared. Sorry, this is not for every, I'm very sorry. There exists z, there exists c. Again, there exists some integer z which is greater than 0, whose square is 2. So domain here, all positive integers. So there exists an integer from that domain, the positive integer. There exists z, such that z squared equals 0. Okay, so these are abbreviations. Now the precedence of quantifiers. The quantifiers such as there exist, for all and there exist, they have higher precedence than any other logical operator. Which means if you see for every this quantifier, the universal quantifier, and you see the disjunction, we must then perform the quantifier before we perform the disjunction. So this here means that, but not this. This is different. This says I first do disjunction between q of x and p of x, then I will say for every x this conjunction happen. But for this case it says for every x p of x happen or q of x alone. There is no quantifier here. So again, when you see for every or there exist, they shall be performed before conjunction or disjunction and before the implication. Okay. Logical equivalences of quantifiers. As we have seen before, statements can be logically equivalent, but here the predicates and quantifiers, they are logically equivalent if they have the same truth value. This is normal. Having the truth value gives logical equivalent. But here, we having different predicates and domain shall not affect this equivalence. I mean, like if we have two equations, one equation equals another, then it does not matter what we substitute for x here or here. If we substitute the same value for x here or here, we get the equality. Or if we substitute the same function here or here, we get the equality. So if we change the function, but every time we substitute the same function here and here, we still have equality. So this is what it means. No matter what predict substituted, this goes for the function. And domain, this goes for variable. And this is the notation. Now, there is an example where we want to show that this quantifier and the product, this composition and this proposition and this proposition, they are equivalent. Now, if this is true, we want to show this is true. And if this is false, we want to show this is false. Now here we start. Now assume this is true. We want to show this is true. Okay? Now, since this is true, let me write it here. For all x, p of x and q of x true. So for all x, this is true. That means p of x and q of x is true for all x in the domain. P of x and q of x is true for every x in the domain. But what makes this true? This is a conjunction. What makes it true? A conjunction is true if both sides of it is true. So, P of x is true for all x in the domain, and q of x is true for all x in the domain. But this means this statement here means that every x, for every x p of x is true. And here q is true for all x. That means for every x, qx is true also. So having this and having this, this is q, this represents we having true and true. So this is true and this is what we want. Okay, now going the other way is to have this to be true. The reverse way, I mean conversely, is to have this to be true, this to be true, and then show this to be true. So it is similar, but we converse the process of the first part. So I will leave it. Okay, negating a quantified expression. So how we do the negation of for every x and the negation of there exists an x. Okay, now This is example presents what is happening. Every student in your class has taken a calculus course. This is statement. How could this statement be false? It could be false if there is one student who did not take the calculus course. Here we go. There is one student who did not take the calculus course. So simply now we got negating this part is negating the universal quantifier, make it existence quantifier but with negating the propositional function itself. Let me write it here. Negating for every x p of x, making that false, means there exists one element such that the negation of p of x happen. There exists one element such that the negation of this x happen. Notice that this looks like moving the negation to the inside of the quantifier, but then changing the quantifier to the universal quantifier to the existential quantifier. Okay, I'm waiting this to move. Okay. Now to prove what we got here, we want to show this is equivalent to that. Okay, let's start. We assume this is true and show this is true. Okay. Now, if this is true, of all of that is true, it consists of two parts. Negation of something. I want to be true. That means what we are negating here, which is this part, it must be false because we are assuming its negation is true. So this part is false. What is false? There exists for what is false? For every x, there is p of x happening. For every x, p of x happening. We are saying this is false. What make it false? Make it false because there is x such that p of x is not happening. So having this false means there is x in the domain such that p of x is not happening. Good. So that is equivalent for saying there is x. Now p of x is false means the negation of it is true. Okay. So there is x. Here we go. There is x such that the negation is true. So good. So we started from this to be true and we ended with this to be true. Okay, I'm waiting my computer to move this, hopefully, please. Oh, my computer is slow. Okay, it's moving now. Thank you. Okay, same thing here. If we want to negate the existential, there exists x such that q of x happening. If we want to negate it, then we will go inside and give the negation to q of x, but then we change the existential to universal. So I'm saying here, we move the negation to the inside here, but we change the existential to universal. And here we go. And the proof of this is the same as the proof of the above one. So I will let it to do. Okay. Now the negation, let's apply the negation on some on some domain, finite domain. So negating, here is the negation. But if we have a finite domain, we already know that for every x, p of x is the same as the conjunction of all of these values. Now, the negation means distributing, and then using the De Morgan's law, we get disjunction of the negations. Okay, but this equals, as we learned before, the conjunction, the disjunction here will be converted to the existential quantifier of what? Existential quantifier of the propositional function which is inside, including the negation. Good. And same thing here, negating an existential quantifier. So this is in place of existential quantifier, and this is the negation. Now we distribute. Now same thing happen, and you may follow that. Okay. So what are the negation of the followings? Negating there exists x such that this happening. So as I said before, take the negation to the inside, and then we have that, and then change the universal to existential. Okay, so the negation of this, x squared is greater than x, the negation is x squared is less than or equal x. So this is, let me use the green for it. This is for the negation, and the existential is here. Now again, this is the negation, and now take the negation to the inside. Inside here. And then we have the negation of x squared equals 2, which means x squared does not equal 2. And here we are changing the existential to universal. Okay. Okay, here let us prove that the negation of this part, so let me make it clear, equals this. We start with it here. Again, what we do, move the negation to inside here. Move the negation to inside here. So we have that. And the parentheses still here. These are the parentheses. And this universal quantifier became existential quantifier. Okay, now how we negate that? Remember, we have from the previous section that the negation of P gives Q is P and not Q. Okay, so this works for P, this is substituted for P, and this is for Q, and then this negation here will give that P of X and not Q of X. So there exists X such that P of X and not Q of X, and this is that part. Now this is an example from Lewis Carroll. P of X means X is a creature. X is a creature. P of X means that a creature is a lion. Q of X means that a creature is fierce. R of X means that a creature drinks coffee. So if you want to say all lions are fierce, so we will say for every creature, if it is a lion, then it is fierce. I will let you think about it. Some lions do not drink coffee, so there exists a creature which is a lion and it does not drink coffee. And here some fierce creature do not drink coffee. There exists a creature which is fierce and it does not drink Nescafe. Okay, and this brings us to the end.